Your textbook did a fine job explaining level curves, but I thought it would be helpful to see a little bit more interactive or um, more visually appealing display of what exactly they were talking about. So this program is Grapher. It's available on any Mac. If you have a Mac, you already have it on your computer. It comes with the operating system, but it's a really good one. I encourage you to play with it if you haven't already. Anyway, let's start off with the curve you see here, which is very similar to one that was done in your textbook. This example is on page 1.11 in chapter 1. Anyway, I've modified it slightly. In the textbook, it was just y squared, not y squared over 4, but I thought this was slightly more interesting. So we can see that we've got these two pieces, one above and one below. They sort of look like mountains, perhaps, and this looks like a valley, the one on the top. The colors are meaningless. They're just there to make it a little bit easier to see what's going on. So don't read anything into the colors. I chose them just to make it look pretty. But what the idea with a level set is you're going to take a horizontal plane and, for example, in this particular case, let's start with just a horizontal plane. This plane is z equals 0. And now I have just a constant set up to make it easier for me to show you. But we have z equals 0, and that's just the xy plane. You can see here's the x-axis, here's the y-axis, it's the xy plane. So yeah, you can see z equals 0 doesn't intersect anywhere. So the level set for z equals 0 is nothing. But if we take z and we increase a little bit, that plane moves up, and shortly it intersects. And now when it intersects, we can look down, and you can see that the boundary of the intersection, right? So this shape right here is clearly an ellipse. And if you made z equal to 2, so this equation became 4 minus y squared over 4 minus x squared is equal to 1, you'd be able to find the equation of that ellipse. And so let's just move up. We can see it's a slightly bigger ellipse, even bigger ellipse. And if we go back down, we can see we have the same exact thing on the other side as it intersects down here. You can see we have some ellipses, and then a slightly bigger one, and again an even bigger one. All right. Now it gets cut off only because the grapher is only graphing a limited range. This does go on forever in all directions. Okay. So we can also take a look, as they did in the textbook, with what happens. Let's put this back to 0. What happens when we intersect with other planes? So let's say if we intersect with the yz plane, which is when x is equal to some constant, or x equal to 0. This looks, you can clearly see looking from the side, that the intersection here looks like a hyperbola. If we turn around the other direction, we see the same thing. Alright, and if we animate this, we see that again, oops, let me go the other direction. Again, we get a family of hyperbola. They're all hyperbola, they're just stretched or shrunk in different ways. Okay. If we look again at let y equal a constant, then we're in the xz plane. In this particular case, we have again a family of hyperbola, but this time they are stretched a little bit. So you can see our family of hyperbola as we go along here. Okay. All right. So that was the example, or very similar to the example from the textbook. Let's just do one more so we can get a flavor of maybe a slightly more complicated function. Here is one. This is x squared plus y cubed plus z is equal to 0. If we look at it from a bunch of different directions, you can probably get an idea just from looking at it what the level sets will be. That's the advantage of these graphing programs. You get a very clear picture without having to do a whole lot of algebra. The idea behind level sets is to algebraically figure out what it would look like so that you could produce these graphs. And it also gives you a better understanding of just the equation itself, the curve itself. So let's take this curve and we'll intersect it. We're going to put off intersecting it with the z-axis just because that's the most fun. We'll start with the intersecting it with x equals some constant. So this again is the yz plane. and let me take my C parameter and bounce it back to 0. All right, and if we look here, it looks like some cubic. And that, I think, makes a lot of sense, because if x is just some constant, then we've got basically z is equal to negative y cubed plus a constant. And as we shift it, it shifts our negative cubic, shifts it up or down. If we look on the other side here, we can see shifts it. All right. So that's what we have when we intersect with the x equals constant plane. If we intersect with the y equals a constant plane, then this one, we have y as a constant, so we've got z is equal to some negative x squared plus a constant, so it's an upside down parabola. If I animate my c parameter, you can see just a family of parabolas. The intersections are all a family of parabolas. Alright. And then the more fun one is the z plane, or the z equals a constant plane. So this one, if we look, it's not a function of x and y. It's, if you make z a constant, we have x squared plus y cubed is equal to negative z, and that's some sort of y cubed relation, the cube root of, y cubed relation. So kind of an interesting looking curve, but that's what that curve looks like. And if we animate our c parameter, you can see that we get even more interesting once we get on the other side. Alright, so that should give you a little bit better idea about level sets.